Hi everyone, welcome to the Lunar Agricultural Test Vehicle team. I'm James Schultz, the project manager, and today I'm going to show you what our mission is composed of. So for context and field interest in the LATV team, firstly, in the NASA 2023 to 32 Decadal Survey for Planetary Science and Astrobiology, American space agencies have implied that they have a huge interest in lunar exploration as a pathway towards cheap development for Martian exploration. The LATV fits as well under the umbrella of the MEP, the Mars Exploration Program, which is an initiative to find any valuable research which would relate to a possible mission to Mars. So on the right, you can see the LATV lander. This lander provides a portable off-world system for testing plant growth in foreign soil. A testbed for extraterrestrial agriculture is needed to improve humanity's capacity for exploration, as food is often our limiting factor when leaving planet Earth. So what you see here on the table next to me is a scaled down version of the real-life LATV rover. This rover serves to gather lunar regolith from the moon's surface and bring it back into the LATV habitat for plant germination. So here you can see a very simplified version of the LATV mission timeline. On day 1, we're launching straight to a translunar injection, coasting for about 3 days, and on day 5 of our mission, we'll be arriving at the moon, at which point we'll be beginning 2 to 3 calibration revolutions to stabilize all of our instruments. On that day 5, we'll be landing, and upon that point, we'll be beginning our 3-week habitat preparation phase, at which point the rover will leave and return to the habitat repeatedly with lunar regolith, preparing the habitat with enough soil to plant our plants. Upon day 26, completion of that phase, the habitat will be sealed, our manufactured atmosphere will be injected to pressurize the habitat, and then for the next 3 months, we'll be observing our plants, and this will be the point of our experiment. Now I'm going to hand it off to Jack Karen, who will talk about our payload.
Hi, my name is Jack, and I'll be talking about the payload subsystem of the LATV mission. Payload covers the plant variety choices, the deployment of plant seeds, and the modification of the soil. Plants were selected for the LATV mission based on their growth spacing, time to maturity, and total water requirement. Our choice of plants are potatoes, radishes, carrots, and soybeans, and they will grow in planter boxes as shown in this figure, based on the spacing requirements for growth, as well as the need for visual contact with as many plants as possible throughout the mission for analysis. The composition of lunar regolith, the soil on the moon, is not adequate for growing plants. Therefore, we will need to bring some additives along on our mission and later mix them in with the lunar regolith that is brought in by our rover. Cocoa coir will be sufficient, as it will increase the permeability of the soil, allowing water to penetrate further to saturate the soil around the deeper roots of the plants. Now, I'll hand it off to Ted, who will talk about our mission launch and trajectory to the moon.
Hi, my name is Ted. I will be reviewing the launch and trajectory of the LATV spacecraft on its journey to Luna. This section will go over trajectory design, specifically regarding port chart plots, launch configuration, and attitude control. Lastly, an animation of the LATV habitat solar panel and landing gear deployment will be shown. Here we can see the timeline of the LATV trajectory. Firstly, a Falcon Heavy rocket will launch from Cape Canaveral Space Force Station in Florida. After reaching an altitude of about 100 kilometers, the spacecraft will orbit a few times about the Earth for system checks. Then the LATV spacecraft will perform a translunar injection burn into an elliptical transfer. Once in the moon's sphere of influence, the spacecraft will separate from the Falcon Heavy second stage before performing several burns to end up in a lunar polar orbit. RCS thrusters will fire for attitude adjustments before landing on the Malapert massive region on the south pole of the moon. For trajectory design, the main goal is to provide the safest, most efficient path between 2 points in space. This path must minimize both change in velocity and time in flight. A common method for achieving this is Lambert's problem, as shown in the figure in the bottom left. If we know the initial and final positions as well as the time of flight desired, we can determine all of the essential characteristics of our trajectory. In order to effectively solve this problem, we can also use Lagrange's solution, which defines a set of constants that can find initial and final velocity changes at the initial and final points based on the transfer angle theta. The port chart plot, as shown in the top left, uses Lambert's problem in Lagrange's solution to produce a contour plot that shows the total change in velocity needed based on the departure time and its subsequent time of flight. Moving on to the launch system, we can see a visual of both the SpaceX Falcon Heavy launch vehicle as well as the LATV lander configuration in the payload fairing. In order to properly fasten the LATV spacecraft to the payload fairing of the Falcon Heavy, orientation is essential. As shown on the right, the lander is positioned topside down to minimize the associated forces it is subjected to during launch. In the table below, we can see a summary of the maximum stress values as well as the minimum factor of safety for each of the lander components. These include the engine, control arm of the leg, upper half assembly, main leg, rover hatch, and service module. Moving on to attitude control, we can see on the right a graph showing the variation in the Euler angles with time. This needs to be developed further with the moments of inertia and angular momentum still needing determination. Finally, we can see an animation of the solar panel and landing gear deployment. Now I'll hand it off to Trevor, who will be going over the structural analysis of the LATV lander.
Hello everyone, I'm Trevor. I'm going to be presenting the structural analysis for the LATV spacecraft. So we're going to talk about the thermal analysis, the landing leg stress analysis, and the habitat reinforcement analysis. Okay, so for our first analysis, we'll start with the thermal analysis of the LATV spacecraft. So we did a SOLIDWORKS flow simulation with solar radiation, and on the left we can see that we needed some type of solution to avoid freezing our plants inside the habitat. So our solution for this was using heat pipes in combination with a thermal coating on the spacecraft, and using this SOLIDWORKS simulation we were able to determine an inside temperature of 53 degrees Fahrenheit, which is well suited for our payload. So for our second SOLIDWORKS simulation, we decided to run a landing leg stress analysis, and what this allowed us to do was simulate a landing impact on the lunar surface. We ranged the impact velocity from 1 to 4 meters per second, and using this sim we were able to determine a maximum touchdown velocity of roughly 2.7 meters per second. In reality this would be a little bit higher because we assumed worst case scenario parameters. So for our second SOLIDWORKS simulation we performed another FEA analysis, but this time on the lander structure. This is going to simulate our launch loading on our vehicle, and the general structure can be seen below. So after running the second FEA analysis on the lander structure, we can see a contour plot on the right here showing our displacements. We ran displacements, strains, and stresses, and we determined that through the sim that under launch loading our vehicle would perform nominally. I'll hand it over to Kyle now, who's going to talk about communications.
Hello, my name is Kyle Klein, and I will be discussing the communications architecture of the LATV mission. The goal of this subsection was to successfully create a communication architecture that could send a data package size of to 2 gigabytes per transfer utilizing X-band phased arrays antennas paired with a transmitter provided by Endurosat. Each downlink would contain photos and habitat monitoring data, while the uplink would contain commands for the human-operated rover. Given that the Endurosat X-band operates at a bitrate of 150 megabits per second, each transfer would take at most 1.5 minutes. Data flows, like the one shown, represent how the downlink to the ground station works. Our lunar module contains GoPro camera arrays along with plant growth sensors, which send the data via the transmitter and phased array antennas to the ground stations. The chosen ground station locations were Australia, Sweden, Hawaii, and Chile. These locations were selected to work in collaboration with the Swedish Space Corporation. A link budget analysis, as shown, was also completed to determine the necessary 13-meter diameter satellites as well as size the data package. After the communication architecture was built, it was time to identify the communication timeline. MATLAB was used to generate a link availability plot and also simulation. The simulation is shown here, and it shows when each ground station has a line of sight with the landing location of the habitat. Each colored line defines when the line of sight is available, and therefore a link is created. The plot here also displays the link availability, but provides time values for these occurrences when the link will move from one location to the next, as defined by the color of each line. Using this information, along with the link budget, a signal-to-noise ratio versus time, and distance plots could be formed, and the results show the created architecture allows for the mission to stay above the desired levels for signal to the level of background noise.
And here finally you can see end-of-life plans for the LATV lander. Our plans include leaving the lander on the moon as a freely available data hub for communication between Earth and the moon. The reason this is advantageous is because our system uses Earth ground stations that are not the DSN, and the DSN tends to be very highly impacted, so this could be attractive for people who need a low-cost option of communicating with the moon. Additionally, the only thing that presents any kind of limit to our time frame in this system is solar panel degradation, which really is a very long time.